Welcome to episode 11. If you're new, this is our Triumph GT6. It's basically a fastback Spitfire with a slightly bigger engine. But since this is a Restomod, we're going to take that formula and enhance it. The whole car is getting a fresh outlook, and last time we kicked things off by announcing our new engine. We settled on an LS4 as it's a unique option and so happens to be the cheapest and smallest all-aluminum LS you can get, but it comes with a few caveats. We swiftly moved through the teardown, as I'm sure many of you've seen it all before, but for a couple of newbies, it went really smoothly, and on the whole, we're pleased with the condition of our unit. So let's get on with today's events and take a look at the intake manifold. The LS4 was designed for a transverse layout, and as such it needed a very low-profile manifold that was flipped, so the intake path actually comes from behind the engine. Fortunately, the design of an LS means we have the option of using it like this, or flipping it back to the typical orientation if we need to. It usually has a plastic cover over it, but we're not going to use that, so we can do away with all these large and ugly mounting bosses to gain back a bit more height. A hacksaw takes off the brunt, and a rotary tool helps smooth out the rest. This rather large breather is part of the PCV system, and it too had to go. What's left is a small hole that goes down into the intake, and generally holes in your engine are not a good thing. Our plan is to come back later to smooth out all these channels and seal up the hole with some kind of filler. These manifolds are made of nylon 6/6, which is plastic weldable, but difficult to fill or bond with other materials. Our current thought is to use an epoxy putty such as Milliput to fill in the voids, but we would welcome other suggestions if you've worked with nylon and have a better solution. In the meantime though, it's helped clean up the look and reduce the size, so let's press on. We're mating the LS4 to a Tremec T5 out of an 04 Mustang V6, using a bell housing from an 85 Jeep CJ. Obviously. For more info on that, check out the last episode. With it all bolted together, we've got a pretty darn tight package that is about the same size and shape as what it's replacing, yet it weighs less, lowers the center of gravity, and makes 3 times the power. This is a really good start, as it takes care of the first 2 large components of the puzzle. Continuing on then, it makes sense to find a new differential and axle shafts, as the current ones definitely aren't up to the task. For a number of reasons though, this raised a problem. Remember the ending to the last video?
We're gonna have to look at that chassis.
Well, we can't push this off anymore. Unlike modern unibody designs, these are body-on-frame cars. They use a chassis that supports the drivetrain components and ties into a structural body shell. The Spitfire and GT6 were based on the Triumph Herald platform, but the Herald chassis was a bit too large to actually fit. To make it work, the sides and back of the frame were cut off, and the overall length was shortened, so what was left was this little thing, which is barely even a foot wide in the middle. If you grab a ruler and twist it, that's exactly what the frame will do if left to its own devices. Triumph engineered the frame and body shell to work together to provide the overall strength, and for 100 horsepower, it's fine. It lacks some pretty critical design features to do a good enough job under an increased load though, which means that our V8 is likely to twist the whole thing into a pretzel unless we do something about it. We spent a while planning out how we could add strength with braces, gussets, triangulation, and maybe even a roll cage. But unfortunately, it all felt like band-aid solutions to an overall bigger problem. So in an effort to add as much strength as possible, we're going to take the obvious route and just not use the frame. Well, not this frame. Like with everything else, it does come down to reason. Since we're not going to use the original drivetrain from the car, why not just sell the entire rolling chassis and build a new one to suit? This way we can engineer something much stronger and avoid any shortcomings from simply modifying our old one. Full disclosure, this wasn't our original plan, but some of the amazing builds on YouTube helped encourage us to give it a shot. We're in for a lot of fun in our small garage, but we're taking that on as a challenge. It's not chronologically accurate at this point in the story, but for interest of clarity, we've already sold off the original drivetrain to a local enthusiast with a bare GT6 shell, so by resto-modding ours, we've also helped get an original GT6 back on the roads, and for that, we feel pretty good. With a custom frame opening up more options, we can return to our hunt for a new differential. Keep in mind, we want to stick with independent suspension. A common enough upgrade is an R180 taken from a Subaru STI. I've owned 2 STIs and I'm overjoyed by the thought of putting parts from one in our GT6. Only we can't. Since we're not using any of the original Triumph suspension geometry, what we actually need to keep things somewhat simple is the entire rear end from another car, not just the diff. Keep in mind the GT6 is pretty narrow. The Mark III is the widest, but still comes within 2 inches of a classic Mini Cooper with factory flares. To make things just that little bit harder, we'd also like to run some dished wheels, as high offset modern ones don't suit this style we're after, and this will mean that the track width will need to be narrower still. As far as we're aware, there is no rear-wheel drive car in existence that has a narrow enough track width and is capable of handling the torque we're making. So automatically, we're gonna have to find something suitable to be narrowed. This poses a whole new problem though, as most cars use CV axles, which may not sound like a problem at first, but keep in mind if you need to narrow one, anything short of cutting and sleeving is going to require whole new shafts to be made, which will run anywhere from $600 to $2,000 around here, which is no. Not to mention that having CV axles will also mean we will either need McPherson or double wishbone style suspension, which takes up room we don't really want to give up. This just left us thinking, wouldn't it be nice if there was a solution that could take care of both of these problems at the same time? Turns out there is. This is a complete Dana 36 rear end from an '84 Corvette. Keeping with our oddball parts hunting style, the Dana 36 is the rear end you don't want. Typically found in the automatic Vettes, it can't handle as much power as the Dana 44s from the manual Vettes and early Vipers. It will, however, handle the power we're going to make, and doubly so as we're not running wide drag radials on a heavy car on a racetrack. Not being desirable means they're available and affordable, and you still get 11.3-inch vented disc brakes, limited slip diff, adjustable camber and toe, domestic parts support, and every major component is aluminum. All of it. As if that's not enough, the main reason why we like it is these. You'll note these are not CV axles. They are UV jointed drive shafts. The suspension geometry can get away with using them without slip yokes because they also function as the upper control arm, meaning there is no need for them to change length. This also means that to narrow this rear end, we only need to have the drive shafts cut down and re-welded, and build some new lower control arms and toe links, which are dead simple to make. So that's not too bad. As narrowing an independent rear suspension goes, it's got to be one of the easiest in the world. As you alter suspension from the factory setup, you do obviously affect the geometry though, so some time will be spent to find the maximum amount of narrowing possible on this setup. Luckily, Corvette owners commonly narrow these in order to fit wider tires, and taking 6 inches out of each side is not unheard of. So with some measurements taken, we should be golden. We felt confident we could make it work, so we bought one, and now finally have enough major components that we can push on with the build. It's taken a solid 4 years to get our poor little GT6 looking like a car again, and we'd simply remove the body shell only at this point if we could. But since we needed to store all the old drivetrain components while we waited for them to sell, it's all got to come apart. Pretty major step here. We've made some room, and the engine's coming out because we're getting ready to separate the body from the chassis, and this is step number 1. So things like wires have been sort of pulled up and out of the way and looped around. Everything that's holding it in at this point is 2 little bolts there and on the other side. So we're going to get the hoist out, get the leveler out, hook it up, and yank her out. Now is probably a good time to go over our plans for the new chassis. The original one necked down in the middle to fit in this recessed area of the body, and we won't be doing that again as it sacrifices too much torsional strength. Instead, we'd like to connect these points as straight lines, but unfortunately there's a floor in the way. We can't chop the car to lower it over the frame because that will actually push the seats up so high that we won't have any headroom. So contrary to the song, we can't go through it, we gotta go under it. Now doing this will decrease our ground clearance, but it's the lesser of the two evils. We mocked up the original 23-inch tall tires where we'd like to see the new ride height and determined there would be room for the rails under the car so long as we don't go too big. 2x4 box tubing was going to be a bit too tall, so we decided to run 3x3 instead. This keeps the same cross-sectional area, but flattens it out for a bit more clearance. With a 1/8 wall, it's pretty stout stuff and should easily cope with the abuse we'll throw at it. Ultimately, we will still have about 4.5 inches or 115 millimeters of minimum clearance, which is only a hair less than the Corvette we took the rear end from, so we can live with that. The plan then is to have 2 large beams running under the main body shell with bends at the back to accommodate the diff. Later, once the body is off the rotisserie, we'll fabricate the front as a second unit and make sure the spliced area is well reinforced. In episode 9, we laid out some rules which absolutely forbid cutting holes in the external bodywork. However, a loophole in that rule allows us to cut out a vast portion of the trunk floor to help get the new rear end and frame in place. The missing piece will be stored away in case we can ever reuse some of it. It's a good thing we didn't waste too much time repairing rust and welding up pinch seams on this piece. I mean, just imagine the remorse to cut it out then. Do note a temporary X-brace has been added to prevent the body shell from twisting while it waits for its new floor. With that material out of the way, we can now test the Dana 36 in its new home to see how things are fitting. What's known as the batwing here is currently a bit wide, but we'll address that later. On the whole, it's fitting in there pretty well, and we can see our way through the next steps. Since we're going to be narrowing it, none of the factory Corvette mounting locations will be usable, so quite a lot of time will be spent in research and mock-ups to ensure the new geometry will still function well. Here's a basic rundown of how the Corvette geometry works. The diff is mounted to the frame here, and to a torque arm that also mounts to the transmission here. The diff itself holds the lower control arms, and the drive shafts act as the upper arms. Together, these control the camber curve the wheels will travel through. The hubs receive the other end of these arms, as well as these trailing links to control the hub's movement fore and aft in the car. Lastly, the tie rods here control the toe of the wheels, and like with the lower control arms, they're adjustable. This is not a short, long arm suspension. Both the axles and control arms are about the same length, but the camber curves are dictated by the distances being different here and here. This causes the wheel to gain some negative camber on up travel and lose a bit on droop. As you might imagine, shortening both effective arms equally will increase the amount of camber gain and loss, but this will actually work to our advantage in keeping the tires inside the fender lips through maximum bump. The trailing links here are not mounted in a parallel configuration as you might think. They're actually designed to point at the car's center of gravity. Doing this creates what is known as anti-squat geometry, which, as the name suggests, is what prevents the back of the car from squatting down on hard acceleration. Squat is not desirable, as when you think of the camber curves, if it does squat, the wheels will camber in and you'll reduce tire contact with the road. You'll also be closer to, if not on, the suspension bump stops, which will make the ride more harsh and less predictable under acceleration. Anti-squat works by using the reactive torque from the wheels to act on the suspension and provide a jacking force to combat the car's weight transfer under acceleration. That's a bit of a mouthful, but you all know the third law of motion: every action has an equal and opposite reaction. When the wheel turns to push the car forward, the hub is seeing the opposite force. That pushes and pulls on the trailing links, and since the arms are mounted on an upward path, they will act to lift the car. Braking will work in contrast and help prevent the rear from lifting too much as the weight transfers forward. It's a pretty cool solution that, in the Corvette's case, accomplishes a lot of tasks with only a few simple parts. Now, we don't know where our center of gravity will be exactly, but we can make a pretty good guess. If we assume we will have improved the weight balance to near 50-50, then it should lay around the middle of the wheelbase. How high above that point is more difficult to guess, but we came up with a number and are going to stick to it and accept the consequences. There are degrees of anti-squat. 100% would mean the car doesn't squat at all. More than 100% would mean the car would actually lift under acceleration, which you don't really want. And less than 100% would just decrease the effectiveness of the geometry. We decided to aim on the safe side and point the arms just below where we think the center of gravity will be. We've covered a lot of stuff here, and I know some of it's just concept, but it's this research and planning that'll dictate whether the car is confidence-inspiring or just a death trap. We could push on more, but this video is long enough already, so I think we'll leave things there and pick up with the new frame build next time. If you'd like to see future videos a day before they come out, check us out on Patreon. Many thanks to those of you who already support us that way. Of course, if you're not already, please subscribe and share this series with some friends, as it would really help us out. Thank you for watching, and we'll see you next time.